Hello students, in last lecture we have studied uniqueness of limit of convergence sequence. We have proved that every convergence sequence is a bounded sequence. Any subsequence of convergence sequence is convergent and converges to same limit. Today we prove relation between monotone bounded sequence and convergence sequences. So we'll take first result. Any monotone increasing bounded above sequence is convergent. So what is the theorem? If Sn n is equal to 1 to infinity is non-decreasing bounded above sequence, non-decreasing means it is increasing bounded above sequence, then Sn is convergent. So we have given Sn is bounded above sequence. Since Sn is bounded above, therefore M is equal to bounded above in R. Therefore M is equal to supremum of Sn where n values in n exist. Which implies Sn is less equal M for all n. 1. We'll prove that any bounded above sequence which is increasing must converge to this supremum. Okay. Plain limit of Sn is equal to M. We'll try to prove this one. Okay. This is 1. So from 1, M is supremum. Means M is upper bound of that sequence and no number less than that supremum means least upper bound is upper bound for that. Okay. So from 1, for any epsilon greater than 0, M minus epsilon is smaller than epsilon, smaller than M, and it must not be upper bound for that sequence. So for given epsilon greater than 0, M minus epsilon is not upper bound, for sequence Sn. This implies for epsilon greater than 0, there exists positive integer m naught such that m minus epsilon must be less than Sn naught. But we know that Sn is increasing sequence. Okay. So now since Sn is non-decreasing, sequence, therefore m minus epsilon must be less than Sn naught is less equal Sn for every n greater equal n naught. Is it clear? Moreover, Sn is okay. Again, Sn is less equal m less than m plus epsilon for every n 3 and 4. From 3 and 4, what we'll get? We'll get m minus epsilon is less than Sn is less than m plus epsilon for every n greater or equal n naught. Sn less equal m gives us Sn less equal m less than m plus epsilon for all n, and we have m minus epsilon less than Sn for every n greater or equal n naught. So from 3 and 4 we get this, and therefore mod of Sn minus m is less than epsilon for every n greater or equal n naught. And therefore limit of Sn is equal to m. So result is proved. So we proved that every non-decreasing means increasing sequence which is bounded above is convergent and it converges to its supremum. What will be parallel result for non-increasing bounded below sequence? Non-increasing bounded below sequence. So what is the next theorem? If Sn is non-increasing, means decreasing, bounded below sequence, then Sn is convergent. So we'll prove this result on same line. Since Sn is bounded below, and therefore infimum of Sn in n exists, and m is less equal Sn for all n. We'll prove that limit of Sn is m. So from 1, for given epsilon greater than 0, m plus epsilon is not lower bound, by definition of infimum, greatest lower bound, is not lower bound for sequence Sn. And therefore for epsilon greater than 0, there exists some positive integer n naught such that Sn naught must be less than m plus epsilon. Again, since Sn is decreasing sequence, is non-increasing, means decreasing sequence, therefore your Sn is less equal, Sn naught is less than m plus epsilon for every n greater or equal n naught. This is my third. Now again from this, so from 1, 3, okay, from 1 and 3, m is less equal Sn, is it clear? So m minus epsilon is less than m less equal Sn less than m plus epsilon for every n greater or equal n naught from 1 and 3, and therefore mod of m minus epsilon less than Sn less than m plus epsilon for every n greater or equal n naught. This implies is mod of Sn minus m this is less than epsilon for any n greater equal to m naught. And therefore limit of Sn is m. And thus the result is proved. So here we have proved that every monotone boundary sequence is convergent. If even though here we proved result for increasing sequence which is bounded above is convergent. Again, what I explain, if this result vary up to conditions vary up to finitely many terms, means the condition for sequence increasingness is true after finitely many terms, means after 1 lakh or 1 crore terms, if Sn is increasing and it is bounded sequence, omit the terms up to finitely many terms where there is a variation. Where there is variation, then that subsequence converges to supremum of that set containing terms of that subsequence after deleting that finitely many terms where there is a variation. What is the limit of that subsequence? It is also limit of this sequence also, because finitely few terms doesn't affect on the convergence of sequence. So even though condition is given here from first term, it is not necessary that condition from first term. So these two results are very important. Now we'll prove this result to check the convergence of some sequences. Okay, we'll take one example. So discuss the convergence of sequence. If Sn is equal to 1 plus 1 upon n raised to n for every n, then show that Sn is convergent. Is convergent. So here we'll prove that this sequence is increasing bounded above. If it is increasing and bounded above, then by previous theorem it must be convergent. Okay. So clearly 0 less equal Sn less is equal to 1 plus 1 upon n raised to n. In fact, you can observe that if I put n equal to 1 here, 1 plus 1 upon 1 raised to n. Okay. Or S's are positive here. Okay. 0 less equal this for all n. So all terms of this sequence are positive. All terms of this sequence are positive. So this is sequence of positive numbers. Right. By binomial theorem, by binomial expansion, Sn is equal to 1 plus 1 upon n raised to n is equal to 1 raised to n, nc0 plus nc1 into 1 raised to n minus 1 into 1 by n plus nc2 into 1 upon n square plus nc3 into 1 upon n cube plus dot up to plus nck 1 upon n raised to k and plus dot up to ncn 1 upon n raised to n. We get this. Now what is the NCR? Using NCR is equal to n factorial upon r factorial into n minus r factorial. From this cancelling the terms n minus r factorial, we'll get this is equal to n minus 1 dot dot up to n minus r plus 1 upon r factorial. Cancelling n minus r factorial there. We get Sn is equal to. So using this NCR, we'll get Sn is equal to 1 plus NC1 is written as n factorial upon 1 factorial into n minus 1 factorial. So cancelling n minus 1 factorial, I'll get just n there. Okay, and that n will get cancelled with n. So this is actually n into 1 by n, right? NC2 is n into n minus 1 upon 2 factorial into 1 upon n square plus NC3 is in this way. We'll get these terms like this. Now what I am doing, I am cancelling this n, taking n outside from this numerator, n minus 1, I will get n square will get cancelled. This term, and this. The n and n cube. This n and n raised to k. Is it right? N and sorry, here it will be 1 upon n raised to n. That terms will get cancelled and we'll get this as 1 plus 1 upon 1 factorial plus 1 minus 1 upon n into 1 by 2 factorial plus 1 upon 1 minus 1 upon n, 1 minus 2 by n into 1 upon 3 factorial plus dot dot up to plus n, 1 minus 1 by n, 1 minus 2 by n and so on, 1 minus k minus 1 upon n into 1 upon k factorial plus so on, what will be n plus 1th term, this will become 1 minus 1 upon n, 1 minus 2 by n and so on. Last term will become 1 minus n minus 1 upon n into 1 upon n factorial. This is a 1. From this also you can observe in Sn, this is your Sn, 1 plus 1 upon 1 factorial, that is 2. So Sn must be greater or equal to 1 minus 1 by n, this is positive. Sn contain a plus b raised to n, expansion contain n plus 1 terms, in which every term is positive, therefore Sn must be positive and Sn is greater or equal 1 plus 1 upon 1 factorial, that is 2. So 2 is less equal Sn. So that is one more observation from this. Now I have to show that Sn is increasing sequence. Sn is increasing sequence. So I find Sn plus 1. Okay. Now Sn plus 1 Sn plus 1 is equal to, in this Sn I am just replacing n by n plus 1, n by n plus 1. So we'll get it is to be 1 plus 1 upon 1 factorial plus this term 1 minus 1 upon n plus 1 into 1 upon 2 factorial. What is the next term? 1 minus 1 upon n plus 1 into 1 minus 2 upon n plus 1 into 1 upon 3 factorial plus so on. What will be the k term? this one 1 minus 1 upon n plus 1, 1 minus 1 upon 2 upon n plus 1, and so on, 1 minus, here k minus 1 upon n plus 1 into 1 upon k factorial plus dot 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 plus k plus 1 n plus 1th term plus last term, this one 1 minus 1 upon n plus 1, and so on, 1 minus n plus 1 minus 1. So 1 minus n upon n plus 1 into 1 upon n plus 1 factorial. In this we will get 1 upon n factorial. In this we will get n minus 1 factorial. This is our, say, 4. 1, 2. Is it clear? Now, r by n, 0 is less than, r by n is less than or greater than r upon n plus 1 for every n. Is it clear? And therefore, minus r upon n is less than minus r upon n plus 1 for every n. Therefore, 1 minus r upon n, this is less equal 1 minus r upon n plus 1 for all n. Using these relations, in 2, 3, we get k plus 1th term, in Sn must be less equal k plus 1th term in Sn plus 1. Sn plus 1. Is it clear? So we are getting this one. Moreover, Sn plus 1 contain last term, or what is that, n plus 2 term, which is positive. This implies Sn must be less equal Sn plus 1 for every n, and therefore Sn is increasing sequence. Sn is increasing sequence. Is it clear? So we'll call this as A. Now if I show that Sn is bounded above, then we are through. Now to show Sn is bounded above. So for this, Sn is equal to, what is Sn? Is 1 plus 1 upon 1 factorial plus 1 minus 1 by n, 1 upon 2 factorial plus 1 minus 1 by n, 1 minus 2 by n into 1 upon 3 factorial plus dot dot up to plus, what is the last term, 1 minus 1 by n, and so on, 1 minus n minus 1 by n 1 upon n factorial. Here if you observe these terms, 1 minus 1 by n lies between 0 and 1, lies between 0 and 1. So if I multiply any number by number lying between 0 and 1, resulting product must be less than that number. This product is less equal 1 upon 2 factorial. This number lies between 0 to 1. This lies between 0 to 1. Their product lies between 0 to 1. Therefore, this number lying between 0 to 1 multiplied by 1 by 3 factorial must be less than 1 by 3 factorial. So this is less equal 1 plus 1 upon 1 factorial plus 1 upon 2 factorial plus dot dot etc. up to plus 1 upon n factorial. Now I can write this as again 1 plus 1 upon 2 raised to 0 plus 1 upon 2 factorial is nothing but 1 upon 1 into 2. 1 into 2, it is less than 1 upon 2 raised to 1. What is your 1 upon 3 factorial? 1 upon 3 factorial. This is nothing but 1 upon 1, 2, 3. So this is less equal 1 upon 2 into 2. Because 1 by 3 is less than 1 by 2. So this is 1 upon 2 square. Right? Similarly for each term, we will get this is equal to 1 upon 2 raised to n minus 1. 2 raised to n minus 1. So this is less equal 1 plus summation of 1 upon 2 raised to n. N is equal to 0 to infinity. Okay. Or I will get n equal to 0 to or k equal to 0 to n 2 raised to k. Now these terms are in geometric progression. Terms in GP with ratio r is equal to 1/2 belongs to 0, 1. So what is that sum? This is 1 plus a upon 1 minus 1 minus r raised to n, that is 1/2 raised to n upon 1 minus 1/2. 1 minus 1/2. Is it clear? This 1 minus half raised to n is again smaller than 1. So this is less equal 1 plus 1 upon 1 minus half. Since 1 minus half raised to n again belongs to 0, 1. This is equal to 1 plus 1/2. Okay. That is 2, which is equal to 3. Therefore, S1 is equal to 2 is less equal Sn less equal 3 for all n. And therefore, Sn is bounded above sequence. From A and B, from A and B, from EB, Sn is convergent. As any increasing bounded above sequence is convergent. It's convergent. Okay. So thus we prove that this sequence is increasing bounded above. Okay.